Assalamualaikum warahmatullahi wabarakatuh. In this video, we're going to extend the ideas that you have seen in the previous lecture notes. Well, previously we have seen what happened when you have a random variable x, and let's say the random variable is discrete. Then we have this following notation. You have learned about fx, which is really the probability mass function, and we also have big F here, which represents the cumulative distribution function, CDF. Now the process of getting this value here and this value is different if you have a continuous random variable. So continuous random variable, you also have the same notation, mathematical notation, but here it represents probability density function, and it will involve integration basically. And here we have also big F. Big F is CDF, cumulative distribution function, and the process here again is related to integrating a certain function. So now in this video, what we're going to look at is we're going to look at this bivariate case. Bivariate means you have two random variables and they are defined together on this like joint sample space. And we're going to consider discrete case because it is easier, and then we're going to follow up with a continuous case. Okay. So in the case of bivariate random variables, therefore we have two random variables that can be defined as x and y. So here we've got two random variables. They are both discrete, and therefore our probability distribution, for example, if x is only one random variable, then we have fx here. So what if fx, in terms of discrete case, it is just probability x is equal to a certain value. Okay. In the case of bivariate, we are going to have this notation. So we have probability random variable x here includes the value x is equal to x, and this is another random variable with certain value of y here. So in other words, we are finding the probability of the intersection of events, so x and y happening together. Okay, to illustrate the idea, consider this simple example here. We have a bottle that contains 3 aspirin, 2 sedative, and 4 laxative caplets. Suppose 2 caplets are selected at random. Okay, and x here, this is random variable, our first random variable. X here represents the number of aspirin, and y here represents the number of sedative that you can get when you draw these 2 caplets at random. So the question is asking you to find the probabilities associated with all possible pairs of values of x and y, and this is the answer given already, but what I'm going to show you next is I'm going to show you how can you obtain this answer. Okay. Now, as I've always said again and again, whenever you are presented with a probability problem and you don't know how to begin, we can always try to visualize the whole problem using a tree diagram, and that is what we are going to do. Okay. So you can imagine opening a bottle of aspirin or sedative and laxative. So there are all those different mixtures inside the bottle, yes. And if you draw one caplet at random, okay, draw one caplet at random. This is the stage where you are going to draw one caplet at random. So draw one caplet the first time you draw that, and the result that you get is going to be either aspirin, you can also get sedative, you can also get laxative. So that's the first time you do it, and you can find the probabilities of that quite easily. So the total number of caplets are 9. So that's total number. And how many aspirin there is? There are actually 3 aspirin. For sedative, 2, and for laxative, 4. So these are the probabilities associated with getting aspirin or sedative or laxative. Next, we are going to continue our process with drawing another caplet, also at random. So we are going to draw the second caplet. So draw the second caplet. And the result that you might get is going to be either aspirin, sedative, laxative. Similarly, for this one, you may get aspirin, sedative, laxative. This one is also the same thing. And there you go. Okay. Now, the probability for this, for this one here, for example, aspirin, the probability of getting aspirin here will depend very much on this event. So we're talking about conditional probability right now. And of course, since the first time you draw a caplet, you will keep it to yourself. So the number of caplets, total number of caplets in the bottle is going to be reduced to 8. So everything here is going to be over 8 basically, yeah. And we need to figure out what's the number to be put on top. So if you have drawn one caplet and it is aspirin, therefore the number of aspirin here is going to be reduced to 2. And if you have taken aspirin at this junction here, so sedative still remains at the original number, which is 2. Similarly, laxative also remains at original number, which is 4. Now, following the same idea, we can see that you have arrived at this junction by taking out sedative. So the number of aspirin is remained at 3. The number of sedative is going to be reduced to 1. The number of laxative is remained at 4. Okay. So at this junction here, you have taken out laxative. So therefore, the number of aspirin is remained at 3. The number of sedative is remained at 2. The number of laxative is reduced to 3. So these are the probabilities associated with all the events here. Now, the next step that we can do is we can list all the sample space. Now we can see that for this path here, the sample space is going to be drawing A and A, aspirin and aspirin. This one here is going to be aspirin and sedative, aspirin and laxative. Here is sedative, aspirin, sedative, 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 laxative. For this one, it's going to be laxative, aspirin, laxative, sedative, laxative, laxative. So this is these are all the possible outcomes, which is the sample space really. Now we're going to turn the elements of the sample space into the associated random variables. So here we have defined random variable x, and random variable y. So x here is representing the number of aspirin. So here is the number of aspirin, and y here is representing the number of sedative. Alright, so we're going to turn our first element here into whatever values related to x and y. So in this case, then you can see these elements here. We've got 2 aspirins. Therefore, the value of x is 2 and the value of y is 0 for this particular element. For this one, we can see that the value of aspirin is 1. The value of sedative is also 1. Okay, so we're just really turning each element into the values associated with x and y. Okay, in the same manner, this is what we can do. We've got 1 aspirin, 0 sedative, because there is no sedative. This is laxative, yes. And for this one, there is 1 sedative and 1 aspirin. This one is 0 aspirin, 2 sedative. This one is 0 aspirin, 1 sedative. This one is 1 aspirin, 0 sedative. 0 aspirin and 1 sedative. And this one is 0 aspirin and 0 sedative. So those are the values of our joint random variables. Okay. So far so good. Yes. All right. Now what we can do next is, okay, so we have got that. So I'm just going to okay, I think I'm running out of space. So what we can do is we can create based on what we've got here. We can see that the values for x has values that are ranging from 0, 1, and 2. Yeah. And similarly, y also has values that are ranging from minimum 0 and maximum 2. And we are interested in the combination of these two values happening together. So what we can do is, I'm just going to use this small space right here. I'm so sorry. So this is going to be quite small. So here we can construct a table, yes, with different values of x. For example, x0, x1, and x2. And then y, 0, 1, and 2. So here we've got like a two-dimensional table. Okay, we are interested in the combination of these values x and y. Okay, so here we've got the table to list our joint probability distribution. Okay, right. Okay, so now let us look at the first one. The first one is this point here, x0, y0. Now we can see that there is only this part here related to x0 and y0. Therefore, the probability of this happening is going to be traced back right here. And you can find the probability can be obtained by multiplying 4 over 9 with 3 over 8. So that is as simple as that. We can get the answer is 4 times 3, 12, 9 times 8, 72. So we got 12 over 72. Of course, you can simplify the answer, but I think I'll just leave it at that because later on I can demonstrate to you. It will be easier to check whether the sums of all these probabilities equal to 1 or not. Okay. So it doesn't matter, you can simplify that or you can just leave it at that first and then we'll see later on what we can do with it. Okay, now for the next one is x1 y0. So we are going to fill up this space, x1 y0. So x1 is here, we've got this situation and we also got this situation. Okay, so there are two scenarios here that we have to consider. Therefore, the probability associated with that is going to be considering these values, you multiply them. And then this one also, you have to multiply these two values. Okay, so here what we've got is 3 times 4 is 12. So we've got 12 over 72. So here we've got 12 over 72. For this one, if you multiply it, you will get the same value, which is 12 over 72. And you add these probabilities up. So 12 plus 12 is going to be 24. So we've got 24 over 72 for that cell. Okay, so for this one here, we've got to consider x equals to 2, y equals to 0. So x equals to 2, y equals to 0 happens right on top here. And for that one, you can see the probability is just this one times with this one. So 3 times 2 is 6. 9 over 9 with 8 is 72. So we've got this one 6 over 72. Okay. All right. Next, we know that for this one, x2, y is 1. There is no way we could get this value because it means that you have drawn 3 caplets because you got two aspirins and one sedative. It is impossible for this event to happen because you only draw two caplets, right? So this event, we can automatically assign the probability is 0, okay? There's no possibility of getting two aspirin and one sedative because the total of caplets is going to be 3, whereas you only draw two caplets at random, okay? Similarly, this is also 0 because here is essentially saying that you have two aspirins and two sedatives. This event here is not happening, 0, okay? For this one is also 0 probability because of the same reason which I have mentioned just now. Now let's move on to the next one, maybe this one. Let's consider this one. This is the event where x is 0 and y is 1. So x is 0 and y is 1. Maybe we can use different color lah. Okay, so x is 0, y is 1, this one. And then this is also a situation where x is 0 and y is 1. So for the first one here, we are going back to this root. So we have to multiply these two probabilities here. So the answer for that one is going to be 8 over 72. And for this one, again, we have to go back and multiply the two probabilities together. So this is also 8 over 72. And we have to add these two probabilities together. Okay, so if you add them up, the answer is 16 over 72. Okay, next we're going to look at this probability, this one here. So 1 and 1, x1, y1. So here is 1 and 1. There's also another one over here. And with a similar idea, go back and find what's the probability. So for this one, the probability is 6 over 72. And for this one, if you multiply these two probabilities together, the answer is also 6 over 72. Don't forget to add these two events, okay, in order to get the real probability, which is going to be 12 over 72. Now, finally, we are looking at this event here, which is y2 and x is 0, which is this one. This is the only event left. And the probability of that is 2 over 9 times 1 over 8. So this is 2 over 72. So this is the table which you have seen obtained in this answer part over here. So that's the probability. And you can see that this is definitely the joint probability distribution because all the probabilities are non-negative, and if you add them all up, 12 plus 24, 6, 12, 16, 2, you will get the total is going to be 72 over 72, which is equal to 1, right? Okay, that's the idea of joint probability distribution. Now let's move on to the formal definition. So again, in this case, we have x and y, and there are two discrete random variables. Therefore, we are interested in this item here. So you can see that when x is discrete, you are interested in probability mass function fx. But now we have x and y, and so we are interested in the combination of them together, x and y. So we are going to write it in this manner, and this is what we call the joint probability distribution, or sometimes you can also call it as joint probability mass function. Okay, now note that this function here or distribution here, probability distribution, should fulfill the following conditions, which is being greater than or equal to 0, and when you add them up, the value must be equal to 1. So if we go back to this example here, you can see that all the values here are non-negative, and if you add all the probabilities here, the answer is going to be equal to 1. Okay, Right, I think I will stop here and maybe I'll continue later on in the next video with more examples related to uh, bivariate discrete case. Okay, thank you very much for watching.